Welcome back to Codex. Our speaker is Dustin Mixon, who is an associate professor in the math department at the Ohio State University. Professor Mixon studies applied harmonic analysis and mathematical data science. Today, he will tell us about Bilipschitz invariants. Take it away, Dustin.
Can you guys hear me okay? All right, so we are talking about some work that I've done recently with Jameson Cahill, who's in the audience, I think, and also Joey Iverson. We've been thinking about the certain circle of ideas for about maybe a year or two at this point. And I think it's a really exciting problem. And I hope that you become excited and start thinking about this circle of ideas with us. So the task is to process some data that is given to you from some real Hilbert space, okay? Some of us are experts in processing such data. Maybe you're familiar with like frame theory. You'll use that to process a vector in a Hilbert space. This has a little twist to it, this problem that we're thinking of. Jeannie is telling us that we ought to identify points that reside in a common orbit of some group of, some subgroup of the orthogonal group of our Hilbert space. And we're told what the group is, okay? The Jeannie's really nice in telling us all of this. So maybe you don't believe in genies, so you want to understand how this could be realistic. Let me give you an example. Suppose we're interested in simple graphs, okay? This is the object of interest. This is a thing that I want to do data processing to. You might notice that this object is not a member of a real Hilbert space. So some work needs to be done in order to encode this as a vector. And what folks will do is they will label the vertices, and they will use that as a way to inform how to make an adjacency matrix for this graph. Now, the choice of labeling determines the adjacency matrix that comes out. So I could have labeled the vertices in a different way and end up with a different adjacency matrix, okay? Both of these adjacency matrices are members of a real Hilbert space, specifically the 3x3 symmetric matrices. And they represent the same object. They represent the same simple graph. The representation is not unique, but it is unique if you mod out by a group of isometries, a group of members of the orthogonal group of this big honkin' vector space, okay? In this case, the group is going to be isomorphic to the symmetric group on 3 letters, okay? So for any 3x3 permutation matrix, you can conjugate this matrix by that guy and come up with another member of this orbit. This is an example of a member of that orbit, okay? So we have this idea of representing objects as members of a Hilbert space, but that representation comes with some ambiguity. And this ambiguity is explained by the action of some orthogonal group. So with thinking about these representations, it's natural to figure out how to compute some notion of distance between objects of interest, okay? So it turns out that the correct choice is defined as follows. So we have this bracket X thing. This is going to be a set, a subset of V. You'd like it to be the orbit of X. It's actually going to be the closure of that orbit. This is a topological closure under the topology determined by the inner product. And then we have this funny looking double quotient type of thing. This is going to be the set of all bracket X's. Okay, so V is partitioned into these bracket X's, and the set of those bracket X's is what we're thinking about. I want you to think of this double slash as I'm really doing two quotients at the same time. The first quotient would be passing to these orbits, and then the second quotient is going from the pseudo metric that's determined by that first quotient. The pseudo metric will identify different orbits possibly, and so we just glue those together, and it turns out that since our group acts as isometries, it suffices to just take this topological closure. So the metric we end up with can be expressed pretty tidily in terms of the orbits. You take the infimum of points from those two orbits, the distance between those representatives. Okay. The reason this metric quotient, we'll call it, the reason the metric quotient is the correct thing to think about is that any continuous G invariant map is going to factor through this metric quotient. Okay, and that's going to be useful to us in a moment. So our task, I'll remind you, our task is to take points from our data set and do some sort of data processing. We want to somehow go to information space. So this is going to be a member of information space will tell us like a clustering that we're interested in, or maybe a classification label that we're trying to identify. So this map, since our data resides in a Hilbert space, there's lots of algorithms available at our disposal. Hilbert space is essentially Euclidean space, and machine learning loves interacting with data in Euclidean space. But now we have to reconcile what the Gini tells us. The Gini tells us that we should really be thinking about our points as residing in the metric quotient. Okay, so this is a metric space, but it's no longer a Hilbert space. So we're missing out on all of those algorithms that have been designed specifically for Hilbert space. We're wishing we could use this arrow. This is most data processing algorithms. Are given from some Hilbert space. If I could somehow figure out how to convert this metric space into a Hilbert space, then I win. And that's what we're going to do. We're going to figure out how to embed our metric space into this Euclidean space so that we can make use of all of those data processing algorithms. Okay, that's the move. Questions so far? Okay. So what does it mean for a map from a metric space to a Hilbert space to be good? Well, in general, there's a notion that you can get for any function from one metric space to another. You can talk about Bilipschitz bounds. Okay, these are going to be numbers, alpha and beta, with the property that for any x and x prime in the domain, you can look at the original distance in the domain space. You can also look at the distance between the corresponding points in the codomain space. And it turns out that alpha and beta give you bounds on how different the original distance can be from the new distance. So every map between metric spaces is going to have Bilipschitz bounds, possibly zero, possibly infinity. But if those bounds are strictly between 0 and infinity, then we will refer to the map as Bilipschitz. Okay, some nomenclature for you. There's a notion of distortion. The distortion is how small can you make this quotient? Okay, so some people will always think of alpha as being 1, and then they're just infamizing the upper Lipschitz bound. This number will exist even if you're not by Lipschitz. If you're not by Lipschitz, that number will be infinity. If you are by Lipschitz, it'll be some number between 1 and strictly less than infinity. Okay. When it comes to distortion, smaller is better. In particular, when going back to this this workflow, the smaller the distortion of this arrow, the better this workflow is gonna perform. Okay, and there exist theorems of this form for various data processing algorithms. Okay, so smaller is better, and the smallest it could possibly be is 1, right? And when the distortion is 1, that's saying something very special about your map. Not only is it by Lipschitz, but it's an isometry. Okay. So the question that we're interested in answering is, how do we by Lipschitzly embed our metric quotient into a Hilbert space? At the moment, we're not going to be terribly worried about the dimension of that Hilbert space. We just want to know, how do we embed it into some Hilbert space? What does it take? And there's a variety of results that are known and a variety of results that are delivered by the project I'm talking about right now. And it breaks out nicely into this Punnett square that cases on whether the dimension of your Hilbert space is finite and whether the group of isometries is finite. I'm going to briefly review some of these. So one thing that we know is that whenever your group is finite and you're dealing with a finite dimensional Hilbert space, max filtering is going to deliver a by Lipschitz embedding. You need the dimension to be sufficiently big for this to work, but there does exist a dimension for which it does work. And what max filtering does is it maps your bracket X to the following. So you have a bunch of templates, you have n of them, and you're going to compute this quantity, the supremum of this inner product over the orbits. Okay. This was the content of Jameson's most recent codex talk. And I don't remember if he mentioned this, but it's an open problem whether max filtering delivers by Lipschitz when the group is infinite. We believe that it's going to be by Lipschitz in this setting. In fact, it is known to be injective once the dimension is at least twice the dimension of the original space. Yeah, it's still an open question whether it's by Lipschitz. Another useful case is when the group that we're modding out by is a reflection group. So for example, the usual representation of the symmetric group on n letters acting on Rn. So just all permutations of the coordinates. When it comes to a reflection group, you can map your bracket X to the unique member of bracket X that resides in your favorite wild chamber. This ends up being by Lipschitz. In fact, this ends up being an isometry. Okay, so this is an example where you can actually get an isometry to come out. There are examples of groups where when you take the metric quotient, it ends up being equivalent to a quotient with a finite reflection group. And since whether something is Bilipschitz only depends on the quotient. We have this result. For example, you could have the orthogonal group acting by conjugation on all symmetric matrices. That quotient corresponds to just Rn modulo Sm. So same thing. So this is what is currently known, and now I'm going to tell you some things that come from the project that I'm currently talking about. So we're able to explain what happens when you have a finite subgroup of SO2. Here V is just R2. So we have an understanding of that. We have an understanding of real phase retrieval. In particular, we understand real phase retrieval even when the dimension is infinite. Jameson has a paper with Ingrid and P. Kazaza that says that in this setting, the standard phase retrieval measurements fail to be Bilipschitz, but we're able to devise a Bilipschitz map that actually goes through. We're also able to do complex phase retrieval. We can treat little L2 of the naturals modulo all permutations of those naturals. Okay. This is a really weird case to think about, and we're going to get to it at the end of today's talk.
Dustin, can you
Yes.
characterize what you mean by permutation? Are you only moving finitely many points?
No, arbitrarily many.
Okay, thanks.
You got it. We're also going to think about little L2 of the integers modulo translations. Okay. Maybe you've caught on to my notation. This is going to be the subject of an open problem. We don't know whether this embeds, but we have some interesting results that say if it does embed, well, we have interesting results. I'll get to it later. Okay. I want to bring your attention to these examples. These are useful examples to think about. They both have a feature that may be surprising to you. They are not differentiable everywhere. So here you think of taking, this is like doing max pooling. So whenever you have, whenever X is such that there are multiple P's that achieve the maximum, you're going to have a kink in your function. Similarly, whenever X resides on or near the wall of your Weil chamber, you're going to be in proximity to a kink. So there's you're not differentiable, and this is this contrasts significantly with what people usually think about in this world, which is algebraic invariant theory. The lion's share of invariant theory up to this point has strictly focused on polynomial invariants, and those are all differentiable. And the ones that I'm telling you about are not differentiable. So what gives? I want to tell you what gives. So let's suppose we have a differentiable G invariant map from one Hilbert space to another, okay? And we're going to fix a point in our domain. There's this notion of Fréchet derivative. I want you to just think Jacobian. So pretend these are finite dimensional, and this is the Jacobian of f at x, okay? It's a linear map from V to W. Turns out, and maybe this isn't surprising, turns out for any member of the stabilizer of x, if you precompose, you'll end up not changing the Jacobian. Okay, this is local symmetries end up being transferred to the derivative. You might suspect this. Locally, certain directions look the same. Okay. So what it turns out, you can do a little bit of linear algebra and show that if you have a member of the stabilizer that's non-trivial, so not the identity, there's going to be a direction that the derivative sends to 0. Okay. There's a direction that locally you're not changing the output. One way to think about this is if I move in the direction of V from X, I'm not going to change the output by much. Okay. We normally think of this as a scalar. I want you to think of this as a vector that goes to 0 as t goes to 0, like t squared. Okay. So locally, it's flat in that direction. And this is bad news for lower Lipschitz. Okay. So for finite G, if I have a differentiable G invariant map, I take a point that has a non-trivial stabilizer. Remember, this map factors through the metric quotient. I refer to the other factor as this F down arrow thing, whatever. This guy is not lower Lipschitz at bracket X. Okay. Does anyone have a question about what's going on right here? So there's a particular point that always has a non-trivial stabilizer, and that is 0. So that means if you're going to be bi-Lipschitz, then you're not going to be differentiable at the origin. Okay, so you're already not going to be differentiable somewhere. And depending on the group, you might be not differentiable in other places. What this indicates is that not being differentiable, this is not a bug. This is a necessary feature in order to be bi-Lipschitz. Okay. It also tells us that the polynomial invariants that we know and love are not bi-Lipschitz. Okay. So all of the invariant theory that's been developed is not useful to the data science problem we're trying to solve. And that is interesting. It's exciting. I hope you're excited. There's gold on the streets. Okay. So all of this analysis that I've shown you so far required a finite group. This is so that I can transfer information about this being flat in a certain direction to being flat even after quotienting. You could imagine if instead I had a continuous Lie group, that this direction of flatness is coming from part of the ambiguity of the group. Okay, so it's actually an open problem of what you can say in the case where your group is infinite here. Okay. Okay. So I just told you that polynomials are not well suited for our problem. It turns out there's a way to fix polynomial invariance. So not all is lost. So suppose I have a function defined not on the full space, but on the sphere in that space, okay? And I take the metric quotient with G, and it's mapping to the sphere of some other space. Once you have that, there's a notion of homogeneous extension you could have. It's the notion that you would independently invent if you had to. This thing is going to map any member of the metric quotient to W, and what it's going to do is, I need to come up with what F is going to do at this point. I'm just going to take it to be C times whatever F does to bracket U. Okay, so this holds for any unit vector, and C is going to be non-negative. Okay, so this determines a function that's defined over the entire space. Notably, I'm starting with a map that's defined on the sphere, and I told you before that the origin was a problem point. Somehow this is avoiding that problem point. So maybe if I have a polynomial defined on the sphere, I can take its homogeneous extension and get something good. It turns out that if f has optimal Bilipschitz bounds alpha and beta, then its homogeneous extension is going to have optimal Bilipschitz bounds given by these numbers. Okay. So Bilipschitz implies Bilipschitz. We can use this to prove, well, we can use this to isolate our attention to the sphere. So we're going to look at this theorem. So finite groups, the following are equivalent. G is going to act freely on the sphere, which is to say that there are no points with a non-trivial stabilizer. What that means is we're avoiding that non-differentiability condition from the previous theorem. Okay, so if G acts freely, there's going to be an n for which there's a Bilipschitz polynomial that sends the sphere in Rd mod G to Rn. Okay, so there's some choice of n polynomials that that act Bilipschitzly on the sphere. And the last thing is you can actually take n to be 2d minus 1. Okay, these three statements are equivalent. And let me walk you through the idea of the proof. First, if C holds, why does A hold? We'll look at the contrapositive. If there's a point with a non-trivial stabilizer, then ideas from the previous theorem give us that there's not going to be a Bilipschitz map. So this is that non-differentiability theorem. It's not literally the theorem that I presented to you, but ideas from that theorem prove a more general theorem that imply this one. Okay. B implies C. This, how do I go from some n down to 2d minus 1? It turns out you can apply a generic linear projection. It's like Johnson, Lin, and Strauss, but algebraic. And then finally, A implies B. Why is it that just because I act freely, it means I have this Bilipschitz polynomial? Well, you get a polynomial that's injective thanks to the work of Hilbert. Hilbert says that the generators, any choice of generators of your polynomial ring are going to do the trick. So that gives you injective. In order to be Bilipschitz, you also need to be an immersion. So it suffices to have control over the Jacobian at any given point. So we do moves involving Lagrange interpolation. And then we do a compactness argument. So it's useful that we're dealing with the sphere and RD in particular. What's more, we can actually, so this is some abstract nonsense. It's an existence proof of polynomial stuff. You can get something explicit in the abelian case. We actually deliver d squared explicit polynomials that do the trick. N equals d squared here. Okay.
Dustin, I think there's a question.
Yeah. Go ahead, Jonathan.
Sorry, let me unmute. Yeah, from the data science point of view, Hilbert space is kind of wrong because it's got the origin, everything's linear. You guess you want to go affine or projective. So with what you just showed about on the sphere, do those equivalences carry over if you pass to a projective space?
So
Quotienting out by the antipode.
right? So in particular, if your group includes negative identity, then I think that what you want actually corresponds to what we're doing. Does that answer your question?
That sounds good, yeah.
So that's actually a fantastic segue. Also, my iPad decided to jump out of the Zoom room. So I'm glad you asked your question at that time, because it gave me time to figure out how iPads work. So here we go. So looky here, we're looking at a real Hilbert space, and I have the negative identity in my group. In fact, that's the only thing in my group. So it turns out that you can create a map from the sphere mod the group into the sphere of this tensor space. Let me tell you how to define this thing. So bracket X is going to go to X to the brackets. That's not how you pronounce that thing, to the tensor squared. So X tensor itself. Okay. So I want to convince you that this is Bilipschitz, and we're going to prove that right now. So suppose I have 2 points in my metric quotient that are distinct. So what that means is X doesn't equal Y and X doesn't equal minus Y. Okay. And now we're interested in this quotient of numbers. Okay. This is the distance squared in the output space. This is the distance squared in the input space. Okay. We're interested in how big this quotient can be. That'll be our upper Lipschitz bound. And we're interested in how small this quotient can be. That'll be our lower Lipschitz bound. Okay. So let's think about what's going on here. So it's just the norm squared of something. So I open the square, I get the norm squared of this guy, which is 1, plus the norm squared of that guy, which is 1. That's a total of 2, minus twice the inner product. And the inner product between tensor squareds is just the square of the inner product. So I get this. I'm going to introduce an absolute value for later, but I get this quantity upstairs. Okay, now let's think downstairs. So I have a distance squared. It's really the minimum. This thing is the minimum of 2 possible distances. Our orbits have size 2. How bad could it be? I get the distance between X and Y, and then I get the distance between X and minus Y. Okay, so I'm taking the minimum of these 2 things. And you can open the square in both cases and then observe that the minimum actually equals 2 minus the absolute value of this inner product. Okay. I'm missing a factor of 2 all over the place. Let's fix that. I have 2 copies of a cross term. So 2. All right. So I can cancel off the 2's. Upstairs, I got 1 minus something squared. Downstairs, I have 1 minus something. So difference of 2 squares, you do high school algebra, I guess. And you end up with this. Okay. Let's talk about what values this can take. So if X and Y are orthogonal, it's 0. It can't be negative because this is an absolute value. Cauchy-Schwarz says that it can't be bigger than 1. In fact, it can't equal 1 because of this constraint. Okay, so this is a number that resides in this half open interval. Okay, and those are all possibilities for this number. So what that means is the lower Lipschitz bound is 1. And the upper Lipschitz bound is, oh yeah, I got to take square roots. So I get square root 2. Cool. So this thing is Bilipschitz, and the usual max filtering approach that amounts to mapping this to a bunch of absolute value of inner products with templates. This is not Bilipschitz by a theorem of Jameson with Ingrid and Pete. So this is pretty great. There's a similar story for if V is a complex Hilbert space. I told you that I'm always thinking of a real Hilbert space, but every complex Hilbert space is a real Hilbert space, like it descends to a real Hilbert space just by taking the real part of the inner product. And then the unitaries become orthogonal matrices in that double dimensional real Hilbert space. Okay, so we're going to take our group to be all phased multiples of the identity. So I take complex unimodular, multiply by the identity. This is the complex analog to this guy. And we're going to mod out by that group. And what we're going to map to kind of looks like this, except instead of doing V tensor V, we're going to do V tensor the dual. Okay, so in particular, X is going to be mapped to X tensor this linear functional. I am conjugating on the left because I'm not an animal. All right. Great. So it turns out that a very similar argument delivers the same optimal Bilipschitz bounds. Great. All right. Let's do another example. I got V being the complex numbers. Maybe you prefer to think of that as R2. That's fine. My group is going to be these rotations by 2 pi over R radians. Okay, so like the way to think about this, a way to think about this is like I have a point here, maybe R is 4. So I move along and then I jump back after going pi over 2 radians. That's how I think about it. So it's as if I need to glue this axis to that axis to create like a cone or something. Okay, so I can embed this into the sphere in R2, so the unit circle, just by raising X to the rth power. Okay, here I'm viewing X as a complex number, so I can actually write that. So it turns out that after doing some annoying trigonometry and calculus, you get a lower Lipschitz bound of this thing. I've never had to pronounce cosecant in a talk before, but okay, cosecant of that thing, and the upper Lipschitz bound is R. These are the optimal Bilipschitz bounds. And these are all examples where the group acts freely on the sphere, and we're able to compute these numbers. It's open what the bounds are for other free actions. Okay. Okay. So how good are these? These are Bilipschitz. Are they the best Bilipschitz possible? Maybe there's better ones. Remember, we had a notion of goodness, it was the distortion. So the quotient of the upper Lipschitz bound to the lower Lipschitz bound. Can I make those quotients even smaller? Well, the Euclidean distortion tells you how small that could possibly be. So the Euclidean distortion of a metric space X is called C2 of X. It's defined to be the infimum of the distortion of F. And what am I taking this infimum over? I'm taking the infimum over all possible Hilbert spaces and all possible maps from your metric space to that Hilbert space. So this isn't an infimum over a set. This is an infimum over a class, but whatever. It's the best you can get by embedding into a Hilbert space. Here are some magical properties of Euclidean distortion. It's finitely determined, which is to say if you pass to a subset, a finite subset of X, and you figure out what the Euclidean distortion is for that finite subset, take the supremum over all finite subsets, it's going to equal this Euclidean distortion for the full metric space. I find that remarkable. Another remarkable thing is that for each of those finite metric spaces, there exists a semi-definite program that kicks out the optimal distortion, the Euclidean distortion. So you can use this information in order to prove the following. Those three examples I showed you, they're not just Bilipschitz. They are Bilipschitz with minimum possible distortion. It's not possible to produce something that's any closer to an isometry in those cases. Those are the best. We can also ask questions like, what's the Euclidean distortion of other metric quotients? I have two particular metric quotients that I'm interested in. I'm going to share those with you, and then we'll close the talk. So first, consider little L2 of the naturals where the image space isn't necessarily R, it's going to be RD. So these are sequences of vectors in RD where the norms of those vectors are square summable. Okay, and we're going to mod out by permutations, not just permutations of finite things, it's just all bijections of n from n to itself. This is an interesting metric quotient because it's an example where it's actually important that you take the closure of the orbits. So there are moves you can do that feel like Hilbert's hotel that send you to members of the quotient by moving along this orbit. So it's kind of interesting, but I'll stop boring you and get to the course. So the theorem here is if D equals 1, so this is sequences of real numbers, we know what the Euclidean distortion is. It's 1. Okay, we constructed an isometry of these guys into little L2, and it amounts to essentially sort, like you sort the numbers, and that gives you something in little L2. Now, sorting naively is going to give you a hard time because there are both positives and negatives in your sequence that you have to wrestle with. But you basically sort the positives in the odd coordinates and sort the negatives in the even coordinates, and that gives you a representative of this bracket X with the same, by passing to those representatives, you preserve the norms. So that's neat. Another neat thing is when D is at least 3, we also know the Euclidean distortion. The Euclidean distortion is similar, just kidding. It's the opposite. It's infinity. It's impossible to embed these into any Hilbert space, no matter how big. And when I saw this, I was surprised because it's pretty different from 1. This is the first example that I've seen of a metric quotient that does not embed into any Hilbert space. It means that this theory is all of a sudden super interesting. Like you might want to characterize the metric quotients that can be Bilipschitzly embedded into a Hilbert space. Obviously, there's a gap. We wonder what's happening when D equals 2. We don't know. Okay, I'm going to close with one more example. So we're going to take little L2 of the integers, and we're going to mod out by translation. So here, gamma is going to denote the Euclidean distortion of little L2 of Z modulo translation. So this is an example of modding out by translation, and there are a lot of related problems of modding out by translation. Like maybe your space is the torus and you can mod out by translation in the torus. Maybe it's Euclidean space and you mod out by translation in Euclidean space. Here's a weird thing. Maybe you just mod out by the lattice, the integer lattice in Euclidean space. So you end up with different structure. Here you have little L2 of R2 and you mod out by rotations. You can also think of functions over the cyclic group and mod out by translation in that cyclic group. It turns out that in all of these cases, gamma is a lower bound on Euclidean distortion. And there's an even more general description of cases that exhibit this lower bound. And it's just easier to show you some of the interesting examples that come out of it. What this suggests, so I'm very interested in this quantity and that quantity and that quantity. This suggests that the Euclidean distortion of little L2 of Z mod Z is fundamental, and that's a thing that is worthy of your attention. And it's an open question what this number is. We don't even know if it's infinite. If it's infinite, you can't embed this metric quotient, and therefore you can't embed any of these metric quotients. Okay, and the distortion, the optimal distortion of these things is going to garbage. It's going to infinity necessarily, if this were infinity. If it were finite, it doesn't mean that you can necessarily embed these guys, but it's a useful prospect. I told you before that these distortions are finitely determined, and you can run an SDP on any finite metric space. The best we could do in that direction is to produce a lower bound on this order. So maybe the optimal distortion is like √2 or something, or maybe it's infinity and we just couldn't find a telling finite metric space, but that's the open question. And that concludes my talk. So thank you.
All right, let's smash that reaction button. Are there any questions?
I do have